Okay, let's continue. Where am I? Did I do this one? Where did I finish last time? Finished at 161, so I'm on to 162. Okay, a profit is earned when revenue exceeds cost. The positive profit function is given by that. Okay, so profit is given by 30x minus 0.3x squared minus 250. Find the exact profit for the sale of the 13th. And then the marginal profit estimated. So should roughly get the same answer. Whoops. Yeah, nearly the same. So you're taking about a marginal profit of 22 units when you're produce the 13th. The 13th construction of a skateboard, manufacturing of a skateboard gets you about $22 profit, marginally extra profit. Now, the next question looks a bit tough. So let's just write down everything we have here. So we have this function p of x, which tells you the price for a demand of x products. So if you know the price, you can get the demand, and vice versa. It's a relationship between price and demand. It's an inverse relationship, sensibly enough. As the price increases, the demand decreases. So that's the price function. And the cost function is 75,000, which represents a fixed cost, and then 65x, which represents a marginal cost. And the first question is, what is the marginal cost? Well, that's the derivative, but I've already told you it's 65. So that's 65. And find the revenue and marginal revenue function. So the revenue function, that would be your sales, x sold at price p each, minus cost for x. So let's just see what formula this gives us. Get decimals. Oh, no, it's a bit messy. So that's our revenue function. And then its derivative would be the marginal revenue. Find the marginal revenue at 1,000 and 4,000. So we want to sub in 1,000. And then sub in 4,000. So it's a negative. Find the profit. Oh, whoops. I'm sorry. I said that's the revenue function. That's not, that's the profit function. Sorry. The revenue function is just the money from the sales. That's the revenue function. Apologies. So then that's the revenue function. And then the marginal revenue is that. And now we sub in 1,000. And then we'll sub in 4,000. Did that make the same answer? I don't think so. We'll check. Actually, I can check the answers at the back in a moment. Interpret the results. So the 83rd sale of whatever it is, the cordless power drills or something, that gives you, not the 83rd, sorry, the 1,000th sale would give you an extra 83 bucks. But the 4,000th sale, you'd actually be losing 97. Now we want the profit. Sorry, so the profit, that's the revenue minus the cost. So the profit function and the marginal profit function at 1,000 and 4,000. So at 1,000, 18. And then at 4,000, it's minus 162. Now let me just double check something because I'm really surprised that that's it. I guess it's a quadratic, yeah. I just want to make a graph here of the profit function just to see clearly what's going on here. Now, I must have done something wrong because this company's always making a loss. That can't possibly be right, can it? The company's always making a loss. Its profit's always negative. That's the most unfortunate company. Maybe it is always making a loss. Let's check the answer. So this is 163. Okay, so 65, so that's correct. And then 143x. So yeah, that's right. Minus that. Okay, so that's right there. 143 minus 0. 143 minus. That looks right as well. 83 and minus 97. Yep, that's right as well. And then it's making 83 per drill. But down to 4,000, it's losing 97. Yeah. And then the profit function we have here, and the derivative there, 18 and minus 162. 18 and minus 162. It's right. This is weird. Is this company never making a profit? It's most unfortunate for them. I think it would have been nicer if the example had them make a profit. But anyways, there you go. Okay, now, what have I got next now? Because I think the next one is not a calculation question. A small town in Ohio commissioned an actuarial firm to conduct a study that modeled the rate of change of the town's population. The study found that the town's population measured in thousands can be modeled by that function where t is years. Okay, so, oh, there it is. I have it here already. Okay. Find the rate of change of this here. Okay, that's fine. It's just the derivative. That's minus t squared plus 64. Bring down the power, reduce the power by 1. Yeah, that looks fine. B, derivative at 1, 2, 3, and 4. So that would be 64 minus 1 is 63. And then that'd be 64 minus 4, which is 60. And then that's 64 minus 9, which is 55. And then that's 64 minus 16. Being lazy. 48, of course. And then find the, and interpret the results. So what this here means, after 1 year, we're growing at, how much is it? It's in the thousands, isn't it? At 63,000 per annum. But then this one here, this one is growing at 60,000 per annum. And then this one here is growing at 55,000 per annum. And then this one here is at 48,000 per annum. And then the second derivative here is minus 2t. So then the second derivative at 1, 2, 3, and 4. So that's minus 2, minus 4, minus 6, and minus 8. So this, you can kind of see, the reason they had us do the 1, 2, 3, 4 is you can kind of see the growth rate is dropping. So you would say that the growth rate is fallen by 2,000 per annum per year. So it's not the population that's declining, but the rate at which it's growing that's declining. So that is the rate at which the population is growing is falling. And it's the same for the remaining three, just replacing the 2,000 with 4, 6, and 8,000. That's all that's happening. You can kind of see like 55 to 48, that's a drop of about 7. You know, so this is, it's kind of a nice question that they had you do 1, 2, 3, 4. So it's, I like it. Okay. Next one now, 165. So we've got a sort of bacteria growth going on here. Uh, 3,000. 1 plus 40 over t squared plus 100. 3,000. 1 plus 4t over t squared plus 100. Culture of bacteria grows in a number according to the function nt is that, where t is measured in hours. Okay. Find the rate of change of the number of bacteria. All right, well, that's just going to be its derivative. There we go. Find 0, 10, 20, 30. Okay. 0, 10, 20, and 30. So interpret your results. So what you can see here, after 1 hour, the population is still growing of bacteria. After 2 hours, the population is flatlined. 3 hours, the population is starting to decline now of the bacteria. And again, after 4 hours, it's declining. Let's get these as decimals to help us out here. It's declining, but not as much. So the population is falling by 14 bacteria cells per hour after 30 hours, and then after 40 hours it's fallen at 10 bacteria cells per hour. Find the second derivatives. Okay, so let's differentiate again, and then sub in 0, 10, 20, 30, 40. Interesting. So it starts off with 0, and then it's 10, 0, 10, 20, 30, 40. Oh, I've got one far enough, 40. Yeah, interesting. So it goes negative, then positive. So that means the rate of growth is falling initially, but then picks back up again. So I really want to graph this to see what it looks like. Yeah, interesting. So at 0, we have an initial 3,000, and then it's growing, but the rate of growth is falling off. And then we reach a point here. Where was the 0 population? That was 10. So this is when the population stops growing and then starts to fall. But it's positive again at 30. So if I zoom out a bit, is it going to uptick again? I'm not sure. No, it looks like it's leveling out. So it's finding interesting that these are positive. So it means that I kind of see that. Yeah, yeah, okay. So how can I explain this? Maybe using the analogy of cars. So what happens is, if you think about n being the distance the car has traveled or the size of the population, the growth is the first derivative. That's like the speed, and the second derivative is the acceleration. So initially, we have a high growth and a high population, but then you put your foot on the brake. So that's the second derivative being negative, and it slows down and you stop at the top. And then you get a negative growth still here. So the population is still falling, but it's not falling as rapidly as before. As it's not falling as quickly as it was previously rising. So as we're going down and losing speed, so to speak, and you put your foot on the accelerator, so you kind of dampen the rate at which you're falling. So you can see this graph is not falling as quickly as this one here is rising. So that's the interpretation here. And I'm curious, what if I just sub in a large value? So we're kind of reaching 0 acceleration here. Yeah, and this, I'm guessing this is going to level out at 3,000 perhaps, something like that. Interesting question. Okay, well, the good thing is we have the answer at the back, so we can look at that. Minus 9.6. Yeah, there's minus 9.6. And then I don't have 0 minus 6. Yeah, there's there. The rate at which bacteria is increasing is decreasing. Yeah, yeah. Okay, that's fine. That's fine. And then we'll do one more. I think it'd be good to finish on 166, because then that means we can start on the next page next time, which is some more, looks like Excel question. Technology question, Excel question, possibly for the rest of it. That's fine. That seems like a natural place to wrap it up for today. Okay, so what's going on here? The centripetal force of an object of mass m is given by that formula. Find the rate of change of centripetal force with respect to distance. So the derivative here, so that would be bring down the power, reduce the power by 1. Find the rate of change of centripetal force of an object with mass 1,000 kilograms, velocity 13.89, and distance from the center of 200. So mass 1,000, that's 13.89 squared over 200 squared. Let's have a look. So that's minus 4.8233025. And the unit would be newtons per second, wouldn't it? But they don't specify the unit for force, but it's newtons. And its change would be newtons per second. You could actually figure, and you can also write the units in meters and seconds and kilograms, because if you look here, this this 1000 is a kilogram. This here is a meter per second squared, and this one's a meter squared. So the unit could also be kilogram meter squared per second squared per meter squared. The meter squareds cancel, and that's kilogram per second squared. And that's actually the same thing, I think, because a newton is also the same as a kilogram meter per second. So a newton per second, or maybe it's not the same thing. That's kilogram meter per second squared. So I've lost my meters. So is the rate of change not? No, it has to be. What have I done wrong here? I'm getting hung up on the units. I want to make sure I have them right. Kilogram is the thousands, meters per second, and 200 meters. Okay, so the units would be kilogram meters per second over meter squared, meters squared per second squared. So they cancel. So that's kilogram per second squared. Okay, but a newton, oh, my mistake, I'm sorry. A newton is 1 kilogram meter per second squared. So that would be newton per second is a kilogram meter per second per second. Why am I losing a unit here? Kilogram meter per second squared. Oh, sorry. I've lost the square there, and that's so per second cubed. What am I doing? I'm doing something stupid. Please excuse my stupidity. Let's highlight here. 1,000 kilograms. Meters per second. So meters per second squared. 200 meters. So meters squared. So that's definitely kilogram meter squared per second squared per meter squared. Cancel, kilograms per second squared. Okay. 1 newton is 1 kilogram meter per second squared. So if I wanted to change this into newtons, I'd have to introduce a meter on the top, put a meter on the bottom, and then kilogram meter per second squared. Oh, it's newtons per meter, of course, or newtons per meter, because dF dr is in newtons per meter, not my mistake of newtons per second. And that disaster will end for today. That's the answer. Hopefully correct now with the correct units. You have a choice: kilograms per second squared or newtons per meter. Yep, sorry, screwed that up a little bit at the end. Should have quit while I was ahead. Thanks for watching. We'll leave it there for today, and I'll see you next time.